Welcome to another edition of VirtualX MasterClass with Mr. Kanyile. Today I want us to take a few problems and run with Euclidean Geometry. Remember that it's all about 13 theorems. This 10 plus the 3 grade 12 theorem. The first one says triangles with equal altitude have the ratio of their areas equal to the ratio of their bases. The second one being proportionality theorem. A line drawn parallel to one side of a triangle divides these other two sides in the same proportion. The third one being the similarity theorem. With those 3 plus this 10, you are armed with every solution for your Euclidean geometry. Remember these 2, when you prove them, we said we use your grade 9 congruency. This 3 has something to do with the center. When they say something is a center, you think of these 3 theorems. This 3 has something to do with the tangent. This 2 has something to do with the cyclic quadrilateral. So when you read your statement, it will guide you to where you'll find the solution. If they say particular lines are tangent, the solution will come from this 3. Tan chord theorem, tan radius theorem, 2 tangents from the same point. If they say cyclic quad, there are only 2 theorems. The sum of interior angles of a cyclic quad are supplementary, or the exterior angle is equal to the interior opposite angle. If they talk about a center, think of the center theorem. The angle at the center is twice the angle at the circumference. Angle subtended by the diameter. Diameter passes through the center. It is equal to 90 degrees. Angles in the same segment are equal. As long as they are subtended by the same arc or chord, they will be equal. I want us to look at this next problem. Remember one thing and one thing only. We are being asked the theorems more than what we are being asked there. Calculate the length of AB. This is the diagram that we are given. We are given that line AE. That line is called the tangent. It is the tangent. Line AB is also a tangent. What is this taking me through to? It is taking me to this theorem. I've got 2 tangents that are coming from the same point. It means that this one is equal to that one. Now, given this part, you only look for theorems where you are. Look at AE, it is a tangent. Look at AB, it is also a tangent. And they are coming from the same point outside the circle. Then they are equal. So the first thing that you need to conclude there is that if this is x, this one will also be x, because these 2 lines are the same. They are tangents from the same point outside the circle. What else do I know? All right. I also know, I can also see this theorem here. What is the name of this line? It is called a tangent. And what is the name of this one? It is called a chord. But there's also another theorem that we should always know, that whenever a radius, this is a radius. Remember, this line is a diameter, so half of it is a radius. This is the radius, and this is a tangent. Whenever a radius meets a tangent, we also know that 90 degrees is formed. There's also 90 degrees here. I know this for a fact. All right, that's all that we know. So what is it that we are being asked for to find here? Calculate the length of AB. We're just looking for the length of AB. Remember, this is AB, which is the same as x. In other words, we're just looking for x. Now, I want you to go to your grade 8, grade 9, which is very much important, because when you are confused with grade 11 or grade 12 stuff, think of the theorems that you've learned in grade 9. I can see this triangle. I can clearly see this triangle. What type of a triangle is this one? It's a right angle triangle. Do I know any theorem that has to do with a right angle triangle? Yes, I know. It's called the Theorem of Pythagoras. What is it saying? It says the square on the hypotenuse is equal to the sum of the squares on the other 2 sides. In other words, this side squared will be equal to this side squared plus this side squared. And there's only one unknown there, which is x. So this is doable. Now, once you are done with the theorems from grade 12, number 1, 2 tangents from the same point. If that is x, this one will be x. Number 2, whenever we've got a radius or a diameter, whenever it meets a tangent, 90 degrees will be formed. Once you establish that fact, right angle triangle will come out. Then you'll go to your grade 8, grade 9 and apply the theorem of Pythagoras, which says AC squared. Let's write it down. Your Pythagoras will then be saying AC squared Oh, let me start with AB squared. AB squared plus BC squared is equals to AC squared. Where did I get this one? From Pythagoras theorem. The square on the hypotenuse is equal to the sum of the squares on the other two sides. Let's push in the values. Let's substitute. What do we have in AB? Remember that we're looking for AB. AB is the same as x in this particular case. Let's push in x squared. Plus, what is BC? What is written in BC? It is x plus 7. So it's x plus 7 all squared. This is the same as, what is AC squared? It is 13 squared. Right? I've just done this simple substitution. I know this x squared plus, let's break that one. What is x times x? It is x squared. What is x times 7? X times 7 is 7x, double that, 14x. And what is 7 times 7? It is 49. Right. Let's take this 13 squared to this side. What is 13 squared? It is 169. So it's going to be minus 169. We'll be left with nothing on the other side. Remember, that's where your algebra comes in handy now. Remember, you are just looking for x, AB. Length of AB is the same as x. This AB is the same as x. So that's what we're looking for. Once you find x, you've got your AB. X squared. So I know that I'm going to have two values of x because my x is to the power 2. I'm going to have two roots there. So you go back to your algebra, factorization. Right? Let's look at like terms. What is x squared plus x squared? It is 2x squared. What else do I have? I have 14x, so it's plus 14x. What is 169 minus 49? It's going to be minus 9 minus 9 is 0. 2 120. Yes, it's going to be 120. Right? This is equals to 0. How did you find 129 minus 9 is 0, 6 minus 4 is 2, then we're left with that 1. So it's minus 120. Right, this is what we have. We've got 2x squared plus 14x minus 20. What do we do now? We factorize. What is the first step when you factorize? Is to open your eyes and look for a common factor. You don't calculate it, you just open your eyes and look for it. Something that is common in these three terms. We can see that 2 is common. To make life easier, we divide everything by 2. If we divide this by 2, I will be left with x squared plus, divide this by 2 is 7x minus 120 divided by 2 is 60. This is equals to 0. From here you factorize. You open two sets of brackets equal to 0. You've got x and x. Right, guys, you are looking for factors of 60 that will give us 7. We said those are 5 and what? That will give us 7. It's 5 and 12. Right? If you add or subtract these two, we must get 7. So how do I get 7? If 12 is positive and 5 is negative, that's where we'll be able to get this 7. So this must be positive. The bigger number will take the sign of the middle term. Right, that's what we have. Now we conclude. We're then going to say x is equals to 5 or x is equals to minus 12. These are the two solutions that we have of x. But remember, we're just looking, the questions was very clear. Calculate the length. What is the length? It is the distance. And the distance is always positive. Therefore, whenever you find a negative answer, you reject it. This is not applicable. Therefore, AB will be equals to 5 units. Whatever units that we have been given there, that's how we'll go about finding the length of AB. All right, we're going on with answering our questions. Remember, it is important to read the statement to check what you are given. Remember what you are looking for. Whenever you look at the diagrams, you are just looking for theorems. Remember the 10 theorems. The first 2, a line drawn from the center of a circle, perpendicular to a chord, bisect the chord. A line, the angle at the center is twice the angle at the circumference. Subtended by the diameter, 90 degrees. two tangents from the same point. All those theorems, you look for them in this diagram. When I look at this diagram, I just don't look at it for just looking at it. I'm just checking the theorem. In other words, I'm guided by all these theorems. In actual fact, this is what I'm looking for in that diagram. Do I have anything that looks like this in this diagram? Because that's where the solutions will come from. Now, let us look at what we're given. Watch here. The first question says, the first statement says, RDS is a tangent at D. I want us just to look at that statement. The statement is, RDS is a tangent at D. Do I know any theorems that deals with the tangent? Yes. How many there are? There are only three. There are only three theorems that deals with the tangent. Only three. It's this one. It's called the tan chord theorem. It's this one, tan radius theorem. It's this one, two tangents from the same point. This is where your solution will come from, just from the statement that I'm given that RDS is a tangent at D. Now, when I look for the third one, let's look at the diagram. Do we have two tangents that come from that are coming from the same point outside this circle? No, we don't have two tangents. So that theorem falls off. I'm looking for the third one that deals with the tangent. Whenever a radius meets a tangent, 90 degrees is formed. I'm looking for that theorem. Do I have that one here? Yes, I do. This is a radius. This is a tangent. What is this saying to me? It tells me that this whole angle here is 90 degrees. So if this one is 40, all this one will be 50. Angle D3 and 4 will be 50 degrees, since D1 is 40, the one that I'm given. The third theorem that deals with the tangent, tan chord theorem. Whenever the angle between a tangent and a chord is equal to the angle subtended by that chord in the alternate segment. Do we have a tan chord here? Yes, we do have. Look at this angle here. This angle here, which is 40 degrees. Look at this angle that I'm given here, 40 degrees. This is a tangent and this is a chord. This angle is between a tangent and a chord. It will be equals to the angle subtended by this chord in the alternate segment. So if this is 40 degrees, the other one will also be 40 degrees. This one will be 40 degrees. We just got that from the statement that this line is a tangent, and I look for three theorems. Do I have all three of them here? I only have two. I don't have two tangents from the same point. So from that information, we were able to find that this angle is 40 degrees. We were able to find that this angle is 90 degrees, just from the fact that RDS is a tangent. Let's look at this next one. BC is equal to CD. I'm trying to emphasize the fact that most of the solution will come from the statement that we're given. So if we say BC is equals to DC, let's look at that. BC is equals to CD. I see some kind of a triangle here. What type of a triangle is this? We go back to grade 9. BC equal to CD. What type of a triangle is this one? Is an isosceles triangle. Remember that angles opposite equal sides are also the same. So what is this saying to me? This also is equals to 40 degrees. How did we find this 40 from? From the fact that we've got an isosceles triangle where this side is equal to this side. So the base angles there, or others call them base angles, will be equal, or angles opposite equal sides are the same. So that will be 40 degrees. Maybe let me just stop there, because I can see the center theorem also. The angle at the center is twice the angle at the circumference. I see all those theorems in this diagram. If you go there with an open mind, knowing that all that will be required for you to identify here are the theorems, and there are only 10. Right, first question. 7.2.1, find the size of angle BDC. Where is that angle? BDC. Well, just looking for this angle here. This angle here. BDC. We've already found this angle that it is equals to 40 degrees. But let's find it the correct way. Number one, I'm going to use this theorem, the tan chord theorem. I'm going to find that angle because it is equal to this one. Once I find that one, I will know this one. Number one, you've got to say angle D1 is equals to angle B1 equals to 40 degrees. Why is angle D1 equals to B1? It is because we've got tan chord theorem. tan chord theorem, that is 40 degrees. Once you identify that B1 is the same as D2, then you can find you find D1 is the same as your B1 tan chord theorem. Then you've got to find this angle that we're looking for, which is BDC. How do you find a BDC? You say angle BDC is the same as what? Remember, I'm doing 7.2.1. BDC. It is the same as angle B1. Why is this two the same? Why is BDC the same as B1? Because we've got an isosceles triangle. We're given that BC is equals to CD. We've got an isosceles triangle. Remember, we're looking for BDC. BDC is equal to B1, but B1 is equal to 40. Therefore, BDC is equals to 40 degrees as well. This angle is equals to 40 degrees, the one that we're looking for. It's just 2 marks. It's very easy. Just apply theorems exactly as you see them. Number 2, let's do the second one. 7.2.2. 7.2.2. What are we looking for in this particular case? We're looking for angle O1. Angle O1. Is it O1 first? Oh, no. 7.2.2. We've got to find the value of angle C. This is where C is. This is where angle C is. We're looking for this angle here. Now watch here. What do we call this? This is called a triangle. There are 3 angles here. 3 angles. What do you know about the sum of interior angles of a triangle? This is grade 8. It comes out in grade 12. What do you know about the sum of interior angles of a triangle? They are equals to 180 degrees. So in other words, angle, we're looking for angle C. So we know that angle C, this angle plus angle B1 plus angle D2 is equals to 180 degrees. The reason, sum of interior angles of a triangle. Alright? So C will be equals to 180 minus 180 minus these 2 minus B1. What is B1? B1 is 40 degrees minus D2. D2 is also 40 degrees. So we've got 180 minus 80. So angle C will, what is 100? 180 minus 80, it will be 100. So that's the value of angle C. It is 100 degrees. So we know this value now, it is 100. Right. What is the next question there? 7.2.3. Let's see what we're looking for there. 7.2.3. Calculate the value of A. Where is A? Oh, A is there. How do we do this one? Remember, it's all about theorems, good people. You must be able to recognize. Now watch here. What do we call this? Think of theorems. Nothing else but the theorems. 1, 2, 3, 4. It's called the cyclic quadrilateral. What do we know about the sum of opposite angles of a cyclic quadrilateral? When you add the angles opposite in a cyclic quad, you will always get 180 degrees. You just apply theorem, it will give you solutions. Now, I know that this angle plus this angle will be 180. I know that this angle plus this angle will be also equals to 180. So I use these other ones. Let's do this thing. We know that angle A, we're looking for angle A. Angle A plus angle A plus angle C is equals to 180 degrees. Reason, we've got a cyclic quad. Cyclic, let me just save time. We've got a cyclic quad. What cyclic quad is this? It's A, B, C, D. Cyclic quad A, B, C, D. That's why you say angle A plus angle C is equal to 180. We get that from our theorems. The theorem says this angle plus this angle is equal to 180 degrees. Whenever you've got the sum of 2 opposite angles in a cyclic quad, you'll always get 180 degrees. The only thing that is asked in Euclidean geometry are the theorems, nothing else. All the questions are just checking whether we understand our theorems. Now, right, we just said angle A plus angle C is equal to 180 degrees. Let's go further. Do we know we're looking for A, we're looking for C? So take C that side. So angle A will be equals to 180 degrees minus angle C. Do we know what is angle C? Yes, we've just found angle C to be 100, so it's minus 100. Therefore, angle A will be equals to, what is 180 minus 100? It will be 80 degrees. That is the value of angle A. I always believe in putting whatever you've got, 80 degrees. For argument's sake, somebody who don't see the way that I see things, the way that I see them, let's find another way of finding the same angle A and see if we can find the same thing. Let's work it out here. Oh, let's work it out in this space. Let's find our space here and find angle A. Now watch here. We already know that we must get, for angle A, we must get 80 degrees. Let's check if we look for any other way of finding A, are we going to find the same thing? Okay, now watch here. Look at this angle. This whole angle here, I'm trying to use the tan chord theorem. I'm trying to use this theorem here. This theorem, the tan chord theorem. The angle between a tangent and a chord is equal to the angle subtended by that chord in the alternate segment. Now, with that theorem in mind, let's try and work things out this side. I'm trying to see that this angle is formed by this chord. Now, if I look at this whole angle here, do you see this whole angle here? It is between a tangent and a chord. This line, therefore, is a tangent. This one is a tangent. And that would become my chord. I'm talking about the angle that is between a tangent and a chord. To find the angle equals to this, I've got to take this chord and go to the circumference. Remember, I'm looking for angle A. Now, we can say that angle D1, okay, angle D1 plus, this is D1 plus D2 plus D2. Where is this angle? Angle D1 plus D2. The position of this angle becomes important. It is between a tangent and a chord. What chord? Chord BD. All right, angle D1 plus D2 is equals to the angle subtended by this one, which is angle A. Reason, tan chord theorem. Therefore, angle A will be equals to, what is D1? D1, we are given D1 to be 40 plus D2. What is D2? It is also 40. Therefore, angle A1, angle A is equal to, what is 40 plus 40? It is 80 degrees. No matter how you do it, you will come back to the same solution, because angle A is exactly equal to 40. That's the beauty of Euclidean geometry. You can find different ways of doing the same problem, as long as you are mathematically correct. Let's look at the last problem. We're looking for now angle O1, 7.2.4. We're looking for 7.2.4. We're just looking for O1, angle O1. Do I see angle O1? Yes, I can see angle O1. Where is the position of angle O1? It is at the center. It is here at the center of a circle. Do I have any theorems that deal with the center? Yes. What are we looking for? We're looking for this angle which is here at the center. I can see this diagram here. This is actually in fact what is being asked. We know that the angle at the center is twice the angle at the circumference. The one at the center is 2 times bigger than the one at the circumference. So if you do have the angle at the circumference as 40, what will be the angle at the center? It will be 2 times 40, which will be 80 degrees. And we're doing the same thing in this particular side. We're looking for O1, and O1 is at the center. Do I know the angle at the circumference? Yes, we know the angle at the circumference, that it is 80 degrees. And we know this, it's all about theorems. We know that the angle at the center is 2 times bigger than the one at the circumference. But both these angles must be subtended by the same arc or chord. Let's look at this chord, chord BD. Look at chord BD. It goes to the center. The same chord goes to the circumference. When we have that scenario, the one at the center will be 2 times bigger than the one at the circumference. Let's do this thing. We therefore say angle O1 is twice the angle at the circumference. In other words, if I want to equate them, I must multiply the one at the circumference by 2 so that they will be equal. Angle O1, if I want to equate it with angle A, I must double angle A to angle A. Reason, center theorem. Angle at the center of a circle is twice the angle at the circumference, or just say center theorem. So O1, remember that we're looking for O1, so angle O1 is equals to 2 times. What is angle A? Do we know what is angle A is? Yes, we've just found angle A to be 80 degrees. So it will be 2 times angle A, 2 times A that, therefore angle O1 will then be equals to 2 times 8, 2 times 8 is 16, 2 times 0 is 0. So it will be 160 degrees. So angle O1, this is how you respond to any question on Euclidean geometry. Remember, at the back of your mind, you are being required to check whether you understand your theorems. You just look for the theorem in the complicated diagram. There are so many theorems in this diagram, you've got to be able to pick them out and use them to solve the problem. Thank you. It's important that you should understand that the center theorem cannot always come in a standard position like this one. Here, this is the arc. This arc subtends this angle at the center, subtends that one at the circumference. So the one at the center is 2 times that one at the circumference. Even if we've got a center here and we're talking about this angle here, this angle here, remember this is the arc, this is the arc. This arc goes to the center, the same arc goes to the circumference. So this angle here is 2 times bigger than that one. So you must be able to notice the center theorem even if it comes in this particular way. This angle here is 2 times the angle at the circumference. The one at the center is twice the angle at the circumference. Now let us look at the problem that was taken from the supplementary exams of March 2010. This was question 8.2. We're given, now watch here, we're given that O is the center. Once they say O is the center, I think of the theorems that have something to do with the center, like the center theorem. Check whether we would have a diameter there. In this particular case, remember this is not a diameter because the center is here. This line does not pass through the center, don't make that mistake. The center is here, this is a radius, this is a radius, this angle equals to that one. Those are the things that we know in this particular diagram. O is the center, I think of the center theorem. I see this theorem here, there, I can see it already. Let's move on. Lm is equals to Mn. Lm is equal to M, we're given. Remember, if this line is equal to that one, that means that this angle here will be equal to this angle here. Because this angle will be equal. Angles opposite equal sides are also equal. So the angle that I put the dots there, they'll be the same angle, they are equal. What else do I know? LON is 100. LON, this angle here is 100 degrees. Right. What's the first question that we're looking for? We're looking for the size of angle LMN. LMN. We're looking for this one in blue. We're looking for this one. This whole angle here. That angle is at the circumference. You look at this angle here. Do you see this angle here? Where is this angle? It is at the center. This is the arc. This is the whole arc. It goes to the center. The same arc goes to the circumference. Hence, the one at the center is 2 times bigger than the one at the circumference. So that becomes important. That becomes crucial. Do I know this angle? No. Can I be able to find this angle? Yes. How do I find it? I go to my grade 8. I know the types of angles. We've got 6 types of angles. So this one that starts from here and goes around up to the same position is called revolution. It is equal to 360 degrees. So if this one is 100, then angle O will be what? 260 degrees. So we know that angle O, let's call this O1. Angle O1 will be equal to 260 degrees. Because, okay, let me just do it proper. We know that angle O1, this one, angle O1 plus angle 100 is equal to 360 degrees. What is the reason? Revolution. Right, now watch here. O1 plus 100 is equal to 360. So it's 100 plus what? That will give me 360. So O1 in this particular case will be equal to 260 degrees. So we know O1 is 260. But we're not looking for O1 in this particular case. We're looking for M1 plus 2. LMN, LMN, these two angles. Remember, this one is 2 times bigger than that one. Let's write that fact down. We know that this angle here, O1, this one, O1, is equals to 2 times LMN, right? The angle at the center is twice the angle at the circumference. So O1 is 2 times LMN. What are we looking for in this particular case? We're looking for LMN. We're just looking for that angle here, LMN. Do we know what is O1? Yes, we know O1. So O1, where there's O1, I push into 60, is equals to 2 LMN. We divide by 2 on both sides. Therefore, LMN will be divided by 2, divide by 2. 2 into 2 goes once, 2 into 60 goes 2, 6 goes 3 times, 2 into 0 goes 0. So this is the value of angle LMN. If you look at 8.2.2, we're looking for the value of angle LKM. LKM. We're just looking for this angle here. We want to find the value of this particular angle. Remember what I said to you earlier on. Euclidean geometry, it's all about theorems. Don't look at the complicated diagram. Just look for the theorem you can find there. I can see this theorem there. Look at this one. If I have something like this, I've got this arc or chord. It goes there to the circumference. The same arc goes to this circumference. I know therefore that this angle is the same as this one because they are formed by the same arc or chord. We call that angles in the same segment. And I can see this theorem there. Look at this one. If you use this as the arc or chord, look at this chord. It goes there. The same chord goes here. So in other words, if angle K are 2 ticks, this one will be 2 ticks as well. But this one is also equals to that. So all these are the same. All those 3 angles are the same in actual fact. Now watch here. We are looking for that angle, but we know that this angle subtended by this arc or chord, it is equals to this one. So if you can find this angle, we definitely know that other angle. Number 2. We also know that this angle is equal to that one. Remember, we've just calculated this angle here. We've just calculated this angle here to be 130. This angle is 130. But these 2 angles are the same. And we know from grade 8 that this is a triangle. And this angle plus this angle plus this angle, what does it give us? It gives us 360. We know that angle, we want this angle because this angle is the same as that one. This one is the same as that one. If we can find this angle, we'll definitely know that angle. So let's look for this angle. But this angle is the same as that one because we were given that this side is the same as this side. Therefore, these angles are the same. We also know this angle, it is 130. We've just calculated it there. But we know that angle, this one plus that one plus this one will give us what? 360. We know that angle, this one, angle M, let me call it angle M, plus angle L1 plus angle N1 is equals to 180 degrees. Why is it so? Sum of interior angles of the triangle. Sum of interior angles of a triangle. Right. Do we know what is M? Yes, we know what is M. M is 130. But these 2 are the same. Instead of writing L1 plus N1, if I'm looking for this one, I'm looking for N1, you can call this L1 as N1 as well. So it's plus N1 plus N1 is 2N1 is equals to 180 degrees. So these 2 are the same because they are angles opposite equal sides. Right? Take 130 that side. We're going to have 2 angle N1 equals to 180 minus 130 equals to 50 degrees. 2 times what will give me 50? 2n is equal to 50. It means 2 times what will give me 50? 2 times what will give me 50? 2 times 25. So n1 is standing in the place of 25 degrees. We know that this angle now is 25 degrees. Now watch here. If you take this arc LM or chord LM, this angle is the same as that angle that we're looking for. We are now saying, now watch here, we're looking for LKM. LKM, let's start with it. LKM is the same as this angle here. LKM, this angle, is the same as N1, is equals to N1. Why? Subtended by arc, which arcs LM. So these two are subtended by the same arc. But do we know what is N1? Yes, we know what is N1. Therefore, LKM is also equals to 25 degrees. That's how you go about solving these grade 11 problems. Whether there are circles around, this is what you do. You just look for that. I want us to move on and look at one or two problems that we come out in grade 12. This is Mr. Kanyela once more doing the Euclidean Geometry in the VirtualX MasterClass. We're responding to problems on Euclidean Geometry. At the back of our mind, theorems, nothing else but theorems. The statement becomes vitally important. We're told that M is the center of a circle. Now, if M is the center of a circle, it makes line AB the diameter. Do I know any theorem that has to do with the diameter? Yes. An angle subtended by the diameter is 90 degrees. So it gives me that this angle here is 90 degrees because it is subtended by the diameter. We just got it from the fact that M is the center, and the line that passes through the center is the diameter. What is this line called from there to here? It's called a radius. I'm just looking at theorems, nothing else but theorems. If this is a radius and this is a tangent, whenever a radius meets a tangent, 90 degrees is formed. There is another 90 degrees here. If this is 90 degrees, the other part will be 90 degrees as well. This side. And you're right. What else do we know? We also know that this will also be another 90 degrees. Straight line gives us 180 degrees. There's so many things that we know here. A line from here, okay. ME is perpendicular to AC. ME, or simply tell that this is 90 degrees, it's fine. CDE is a tangent. We're told that this line is a tangent, the radius meets a tangent. There's something that we know here. If this is a tangent and this is a chord, tan chord theorem, I go with this and go to the circumference. I don't go here. Angle between the tangent and the chord is equal to the angle subtended by that chord in the circumference. So I know such things. All right, and I'm told that MB is 2 times BC. MB is 2 times BC. Which one is big? MB is 2 times bigger than BC. Let's indicate it this way. If this is 2, this would be 1. I'm saying this is 2 times bigger than that one. What is the name of this line from there to here? It's called a radius. So what will this one be called? Same thing, radius. From there to here, it's a radius. So we know the things that looks the same, that are actually the same. Let's look at questions. Now that we've looked at the statement and we've got so much information just from the statement. Now let's work it out. If D is equal to X, write down, don't think, don't calculate, just write down 2 other angles equals to X. Where is X? This is where our X is. This is where our X is. Look at the position of that X. Where is X? X is between a tangent and a chord. It is between a tangent and a chord. To find angle equals to X, I've got to go with the chord and move with it to the circumference to find another angle equals to X. So this angle here will be equals to X. So angle A is also equals to X. We're responding to this question. Angle A is equal to X. Why? Tan chord theorem. Let's find the second one. Now watch here. AM is equals to MD. Why are these two equal? Radii. Radius, radius. This plural for radius is radii. Radii. This is plural for radius. So if these two lines are equal in this triangle, isosceles triangle, therefore this angle will be equal to this one. We found a second angle equals to x. Reason angles opposite equal sides are equal. Angles opposite equal sides are equal. So x will be equals to x. So the question says write down two other angles equals to x. It was this one. How do we find this one? Tan chord theorem. Then this one is equal to that one because these two sides are equal in that isosceles triangle. So we've done 9.1. Let's go to 9.2. Prove that CM is a tangent at M to the circle passing through MED. Prove that M is a tangent. Prove that CM, where is CM? CM. This line can goes up to there. Prove that CM is a tangent at M. It's a tangent at this point to the circle passing through M, E, and D. Let's sketch this diagram. It passes through M, E, and D. The question is, I've got to prove that this is a tangent. Now watch here. If I have something like this, I've got a line here. I don't know what this line is. I've got another line there, which is a chord. I've got this one. I've got that one. Now watch here. If this angle here is equal to that angle there, definitely this line will be a tangent because it is the angle that is between a chord and a tangent that will be equal to the angle in the alternate segment. So if this one is equal to that, definitely this line will be a tangent. The question is, prove that CM is a tangent. We want to prove that CM is a tangent. In other words, we want to show that this line, this whole line here, let me do it in red. We want to show that this line is a tangent. All right? Okay. Now, let's look at it. if this was a tangent, let me look at it. It's better that way. Okay. Remember, we found these 90s here, subtended by the diameter. Look at this one. Look at this one. Look at this angle here. Look at this angle. In this circle, this becomes my chord. This becomes my chord of this circle. And you can see the angle M3. It is between this line, which I don't know what it is, that I'm trying to prove that it is a tangent. But this angle here, look at this chord. This chord takes me to this angle. And this angle is exactly equals to 90 degrees. Look at this one. If this is a radius, it means a tangent. 90 degrees is formed. Right? Now, if then this is a chord, the angle between this line and this chord, it subtends this angle here, which is 90 degrees. It makes this angle to be the same as that angle. In the very same way, if this angle is equal to that angle, therefore this line will be a tangent. Now, if we say M3 is between a line which we don't know what it is and this chord forms 90 degrees here at the circumference. Therefore, this angle, if this angle is equal to this one, definitely this line must be a tangent. That's how you go about responding to 9.3, to 9.2. Let's go to 9.3. Prove that FMBD is a cyclic quad. It's concyclic. Remember, there are only two theorems that deals with cyclic quad. It's this one, which says which says this angle plus this angle must be equal to 180 degrees. And the second one, which says the exterior angle, this one, exterior, is equal to this one, equal. But we add those two, you get 190. This one is equal to that. So that's what we'll be looking for in that particular question. Let's look at it. Prove that FMBD is a cyclic quad. For something to be cyclic quad, this angle and this angle must give me 180, or the exterior angle must be equal to the interior opposite angles. Now let's look, where is FMBD? FMBD, let me do it in black. this one, F, M, B, where is D? D. I must show that this figure here in black is concyclic. I'm saying to you, if we have something like this, if this angle plus this angle gives us 180 degrees, it means that this is concyclic. We can draw a cycle around this. Or if I have something like this, if this angle here is equal to that one, therefore there is a circle around here. I don't have to be told. It's the converse of the cyclic quad. Let's work it out. Let's work it out. Look at this angle here. How many degrees is this angle? This angle here. M1 and M2. This is 90 degrees because this is perpendicular to that one. We're given that 90 degrees. Now watch here. Remember in the beginning, we had a diameter. It subtends this angle here, which will also give it 90 degrees. Now we are then asked, is this FMBD concyclic? It will only be concyclic if this angle plus this angle is equal to 180 degrees, or if this one is equal to that one. There are two ways. If I like, I can say to them, look at angle M1 and M2. Angle M1 plus angle M2 is equal to 90 degrees, right? Number two, angle D2 plus D3 is also equals to 90 degrees. Where did you get that one from? Subtended by the diameter AB. Remember that it was subtended by the diameter AB. Now let's add these two and see what we get. If you add M1 plus 2 plus D1 plus D1 plus D2 plus D3. D2 plus 3, what do we get? M1 plus M2, it is 90 degrees, plus D2 plus D3, D2 plus D3, it is also equals to 90 degrees. What is 90 plus 90? It is 180 degrees. What is this saying to me? The sum of these two angles, if they are 180, this will be concyclic. Therefore, UFMBD is concyclic. Converse of the sum of two opposite interior angles of a cyclic quad. So that's how you go about doing it. I want us to look at this last one. Prove that DC squared is equals to 5BC squared. Prove that DC squared is equals to 5BC squared. Prove that, it's about 3 marks, prove that DC squared is equal to 5BC squared. I don't know where to start, but I go back to my grade 8, grade 9. When I see something that is squared, I think of a Pythagoras theorem. Remember that the Pythagoras theorem happens in a right angle triangle. This side squared is equal to this side squared plus this side squared. That's what Pythagoras is saying. The square on the hypotenuse is equal to the sum of the squares on the other two sides. If this is x, this is y, this is r. Pythagoras is saying r squared is equal to x squared plus y squared. This is what the theorem of Pythagoras is saying from our grade 8 and grade 9. Now, prove that DC squared is equal to 5BC squared. Why am I thinking along these lines? Because I see something that is squared. It's pushing me towards thinking towards the Pythagoras theorem. DC squared is equal to 5BC squared. Let's go to the diagram and look at that. DC. I know that for me to use Pythagoras, I must have a right angle triangle. Now, I see DC there. Here is my DC. Here is my DC. This is my DC. Can I create a right angle triangle from here? Yes, I can. Remember, we have this 90 here. From here to here. So if I want to create 90, I must have DC and BC. There is BC there. So I will have to move up from here to get a right angle triangle. To get a right angle triangle, I need to go up here and then close there. This is the triangle that I'll be using. This triangle, let me just shade it in this way. This is the triangle that I'm dealing with. I'm going to prove that in triangle what? MDC. This is the triangle that I want to focus at. Triangle MDC. DC squared, I want to do that, to find what is DC. Is it really 5 BC squared? I can see BC in the same triangle. All right, what is this saying? Let's write the theorem of Pythagoras. This is MC squared is equals to MD squared plus DC squared. That's what Pythagoras is saying. If this is 90 degrees, the side opposite will be the hypotenuse. The square on the hypotenuse is equal to the sum of the squares on the other two sides. But this one started with DC. We know that DC squared, let me write it down so that it will make sense. We know that MC squared is equals to DC squared, right? MC squared is equal to DC squared plus DM squared, or MD squared. Reason? Pythagoras theorem. All right, that's what we have. Can I ask you something? Are we looking for MC? No, we're looking for DC. Let's make DC the subject. Now, DC squared will then be equals to DC squared. This must come to the side. Will be equals to MC squared minus DM squared, because this is coming this side, minus DM squared. Okay, let's look at what we have now and what we want to get. This is where we are running to. DC squared, I've got it here. 5 BC squared, oops, I've got MC and DM. Can I write this in terms of BC? Because that's what we have there. We've got BC. Let's look at MC. Can I change MC to be in terms of BC? Because I see BC, there is no MC there, there is no DM there. Let's change that around. Where is MC? This is MC. Can I express MC in terms of BC? Okay, now watch here. Look at this given here. What is this saying? MB is equals to 2 BC. MB is equal to 2 BC. So if this is BC, MB will be how many BCs? It will be 2 BC and 1 BC. Right? Are given. MB is equal to 2 BC. Where there is MB, you can put 2 BC there. That's the distance there. So, but we want to change MC into BC. MC. How many BCs do we have here? We've got 2 and 1. So this all together will be 3 BC. 3 BC. So MB is 2 BC. BC is 1 BC. So MC will be 2 BC plus 1 BC, which will give us 3 BC. So this is what is equals to 3 BC squared. So we've expressed MC in terms of BC. Now let's work on the other one, which is DM minus DM. Let's look at DM. Where is DM? This one. Can we express this in terms of BC? Remember, we want to have BC. What is the name of this line? It's called the radius. What is the name of this line? It's called the radius. What is the name of that line? It's called the radius. If radius is the same in the same circle. So this distance is the same as this one, the same as this one. And you want to express this in terms of that distance, and they are the same. Remember that MB is the same as MD. Why is these two the same? The radii of the same circle. Therefore, I can remove MD and put BC. Right? How many BCs are these? 2 BCs. So it's minus 2 BC squared through substitution. Right, that's what we have. We only have BCs now. Now, watch here. If I look at this, if you read this, it's 5 BC squared. Is 5 squared? No. What is squared there? It is only BC. I want us to have only BC to be squared and take 3 out of it for being squared. So this is squared will then be equals, let's take this out of being squared. It will be 9. Leave only BC to be squared. It will be 9BC squared. Right, that's what I wanted. I've got to do the same thing that side as well. So this would be minus, because I want to have BC squared, not 5 to be squared. So this 2 must not be squared. What is 2 squared? It is 4. What? BC squared. Now only BC is squared. What does 2 boys mean? It means abafana babili. 2x squared or x squared about 2. 2 sine x or sine x about 2. 9BC squared or BC squared about 9. Minus 4BC squared. How many BC squareds do we have this side? We've got 9. How many are we subtracting? We're subtracting 4. How many are we going to be left with? So this squared will be equal to, what is 9 minus 4? It is 5 of the same thing, of BC squared. It is exactly what we wanted to get. So it is true that this squared is equal to 5BC squared. Thank you.